Greetings and welcome, friends. That's right. Welcome to all of you. Bienvenido. Is that? Sure. Close enough. It's page 454. We were talking about double and half angle identities. Here's question 17. It says, use a half angle identity to find the exact value of each function. So they want us to use a half angle identity. So let's talk about 3 pi over 8 first of all. Let's see if I can gather any information about this. So recall, friends, that pi is, right, full 180 degrees equivalent, right? So if I take this pi and divide it up into fourths, all right, this would be what degree? This is pi over 4, which is the same as what in degrees? 45 degrees. So pi over 8 would be another slice of that. If I slice this in half, this would be pi over 8. All right? And that would then be half of 45 degrees, which is 22.5 degrees. Okay? So if I want 3 pi over 8, first of all, that's less than 4 pi over 8, which is less than half of this. I believe 3 pi over 8 would be right here. Which, if you think about it, here's pi over 8, here's 2 pi over 8, here's 3 pi over 8, right? Something like that. So this is what I'm referring to. So it looks like I'm referring to, what is that going to be? 45 plus 22.5, is that what? 67.5 degree equivalent is what I'm referring to. Okay, and I just want to point out that 67.5 degrees is half of what angle?
135.
Is that 135?
Yes, it is.
Okay, all right. And 3 pi over 8 is half of what angle? It'd be 6 pi over 8, which reduces to
3 pi over 4.
3 pi over 4.
Well, I had that part right.
Okay.
Yeah, why did you need that? Yeah.
Well, you didn't necessarily need it, but I just want to point out, here's 3 pi over 4, right? And technically I'm talking about a half slice of it, all right? So there's 2 halves. Yep. Well, I just want to communicate the radian degree thing, get us all on the same page here so far. Yes. So let's see, I'm using green here. So sine of 3 pi over 8 is the same as sine of 3 pi over 4, all divided by 2. Agreed?
Agreed.
Agreed, right? Because of this. I thought you were calling me show off, but you were saying like sure, I think is what you said. Yeah, sure. I like it. But I think calling a math teacher a show off would be funny too, just like show off. You know the Pythagorean theorem. That's great. Show off. Like I get okay, like I could see that. That'd be funny. But let's keep going here. So the half angle identity I'm thinking of using is probably the one related to sine. So I'm thinking that sine of alpha over 2 is equal to, let's see, it's a plus or minus, we'll talk about that in a moment, all over, of the square root, all over 1 minus cos alpha over, what is it, dos? Yeah, thank you. So it looks like I would want to plug this alpha into this part over here, right? This is what I'm thinking. And one of the things I want to ask you guys is this plus or minus is based off of the quadrant that I'm in, all right? Alpha over 2. So not the quadrant that this is in, but the quadrant that the entire thing is in, or 3 pi over 8. 3 pi over 8 is in quadrant 1, so what is sine going to be? Positive. Also, it would have been positive if it was over here anyway, for sine, right? So I'm expecting this to equal the positive square root of 1 minus cos alpha, which is 3 pi over 4.
Did you also do that with 135? Yeah, that's what I was.
You could have, but I'm going to try to familiarize us with the radians a little bit, just so we are awesome. You would. Now, 3 pi over 4 I've got to find the reference angle to that guy, which would be what? Pi over 4, right? 45 degrees. And is cosine positive or negative in this quadrant?
Negative.
Negative. So cosine is negative. So cosine is negative in that quadrant, right? Something like that. So I believe, friends, that I could replace this with the square root of 1 plus, or minus a negative if you wanted, cosine of pi over 4. Agreed? Let's see what happened to my writability here. Uh-oh. Man, we had some lag there. That's okay. I think I have a 3-second delay on my stream just in case someone gets really vulgar or if there's like a wardrobe malfunction. So let's see. Like, yeah, you know. So let's see. Cosine pi over 4, hand trick. What's that?
Hold on, that's not my hand.
Root 2 over 2. All over 2. This becomes, let's see. This becomes 2/4 plus the square root of 2/4. If I divide this, I get fourths, and then 1/2 is the same as 2/4. We saw some of these fractions a little bit before, so that's why I'm willing to cruise through them a little bit faster. 2 plus the square root of 2 all over 4. Square root top and bottom, I get square root of 2 plus the square root of 2 all over the square root of 4 is 2. And I believe that is our answer. And yeah, problem 17, that's right. Oh, there you go. There you go. So I don't know. Maybe it was a typo in your book. Sometimes that happens. Here's question 19. Let's keep moving along. Same premise. This time we've got tan 22.5. So this is the same as tan of 45 div 2. Am I right? Yeah. The tangent formula, it's plus or minus. Well, let's see. First of all, whether it's 22.5 or 45, it's both in the first quadrant. Tangent's going to be positive. So I'm talking the positive square root of this. Yeah, positive square root of 1 minus cosine 45 over 1 plus cosine 45 should do it. Throw little degrees in there, why not? This did have a restriction that cosine alpha could not equal -1, but that occurs at 180 degrees, not at 45. So we've got no issues there. We just talked a moment ago about cosine at 45 being root 2 over 2. Hasn't changed in the last minute and a half, so I'll assume it's still true here. All right. So this is crazy. This is where all this fraction work comes in. I've got little denominators, as I call them. I'm going to multiply top and bottom by the LCD of the denominators. All right? And that's going to kill all these little fracts. So this would be the square root of 2 minus the square root of 2 over 2 plus the square root of 2. Now I technically, I've got, man oh man, I've got so many radicals floating around. I've got this radical in this denominator. In order to get that out, I actually have to multiply by the conjugate, complex conjugate, not complex, just plain old conjugate, I guess, because these are not imaginary at this point. So I'm going to multiply top and bottom by that. You guys have seen some of these patterns before. This is going to be a squared minus 2ab plus b squared. A squared is 4 minus, actually, you know what? I've got this square root here. It might actually be beneficial for me to just write this as 2 minus the square root of 2 all squared, because the square root will cancel with that for the numerator portion anyway. You know what I'm saying? I think you know what I'm saying. Over 2 plus rad 2 times 2 minus rad 2, a minus b times a plus b is a squared minus b squared. So a squared 2 squared is 4 minus root 2 squared is 2, right, like so. So let's square root top and bottom. So the square root of a square just simplifies. And 4 minus 2 is 2. Looks like I've got a square root of 2 in the denominator. And I'm going to have to rationalize denominators again. Oh my goodness. These tangent ones are always crazy. I love it. So what do I multiply by to get rid of this square root of 2? Square root of 2 over the square root of 2. I like it. And up top I'll distribute, and down bottom these are going to cancel quite nicely, if I might say so. So let's see. I'll have 2 rads 2 minus root 2 times root 2 is just plain old 2, and root 2 times 2 in the denominator is plain old 2. And I can now just reduce pretty much each term by 2. So that's going to be 1 and 1 and 1, right? So I'll just have the square root of 2 minus 1 is my final answer. That would do it. So for this, I just want to point out the majority of this work was not based on your trigonometric pre-calculus understandings. It was all based off of your algebra 2 manipulations of radicals and pattern knowledge. So just be aware of that. Some of that stuff might come back to haunt you. And if you're looking for help on that, my man Salman Khanman can help you out at his website, khanacademy.org. It'd be pretty great. He could show you how to rationalize denominators as that concept right there. Let's look at one last example. I guess the instructions would be helpful for this. They actually want us to find sine 2 theta, cos 2 theta, tan 2 theta. All right, so I'm guessing the double angle identities would be good for this. Now, in this case, they've told me the value of tan theta. Tan theta. Tan theta over 2? No? My book's all blurry here. No, here's the instructions. Yeah, that's what they're looking for on my book. But nonetheless, here we go. Tan 2 theta. Let's talk about what's going on here. Tan of theta is negative 2. What does this mean?
Isn't it 90 to 1 and then 180?
That's the same as 90 and 180.
So
yeah, we're talking about angles in quadrant 2. We're talking about this quadrant here. Okay? Now, notice, if I'm looking for the value of sine 2 theta, all right, I've got, identities for sine 2 theta, cos 2 theta, tan 2 theta. But if I'm looking for sine 2 theta, I actually need to know the value of sine and cosine in order to calculate it. All right, I currently know the value of tangent. Now, to make a bridge between those, I could use some Pythag identity maybe, and reciprocal identity, and then some quotient identity, and figure it all from there. Although in this case, let me just draw a little triangle, a right triangle in this quadrant. Now, tangent is negative 2, it claims, which tells me the ratio for theta, or the reference angle even, right, tangent is opposite to hypotenuse, correct? Yep. And that means that opposite is going to be 2, opposite's going to be 1 if the ratio is 2, right? Do you agree? And which one's going to be negative here? Should it be this one or this one?
Negative 1.
How do you know? Yeah, because it's moving to the left of the right origin, whereas the y value is moving up. So if this is my little triangle, I can actually do some Pythag work on this if I'd like. So negative 1 squared plus 2 squared equals, I don't know, what do I usually call that? R squared maybe. Doesn't matter. That's 1 plus 4 equals r squared. I end up getting r is equal to the square root of 5. I love it when my r's look like 5 square root symbols. It's pretty good. Yeah, not like, well, I guess it looks like a 5 almost this way-ish maybe. But anyways, r is the square root of 5. How is that helpful to me? Well, now from theta's perspective, I could tell you the values of sine and cosine. So sine of theta is going to be opposite to hypotenuse. So that's going to be 2 over the square root of 5. Or, if you're interested, 2 square roots of 5 over 5, whichever one you'd like. Although we're probably going to want the second one because it's all nice and reduced. And cosine of theta is going to be what? Adjacent to hypotenuse. So that's negative 1 over the square root of 5. Or negative rad 5 over 5. And that's the value of cosine. So now that I've found those, which by the way, like I said, you also could have used Pythag identity and reciprocal identities, to go from tangent to sine or cosine and eventually found them all. But let's find out what sine of 2 theta is. Sine of 2 theta, according to the formula, is twice the value of sine times the value of cosine. So let's see, multiply across the top. I'll have, first of all, it's negative. 2 times 2 is 4. Rad 5 times rad 5 is 5. All over 5 times 5 is 25. Or actually, I could just view that 5's kind of canceling out at some point, right? 5 and 25 are just the 5's in one of those 5's. So I believe my answer is negative 4/5, if I'm not mistaken. Did anyone check the answers on these? I don't know if you have that value. Good, good. I like it. Cosine 2 theta. I've got a bunch of options. I'm going to do the 2 cos squared one. So 2 times negative square root of 5 over 5 squared. And what's it, minus 1 if I recall? Yep. So I could have chosen any of the 3 cosine functions since I did already calculate tangent and sine and cosine, although cosine only is based off of either of these 2. So let's see, 2 times, well, the negative all squared is positive. Root 5 squared is 5. 5 squared is 25 minus 1. So that's going to be, 5's cancel out. That's 2/5 minus 5/5 if I want to find a common denominator. So that's going to be what? Negative 3/5. Question, what quadrant must I be in if both sine and cosine are being negative so far? Which quadrant? Quadrant 3 is correct. Yeah, they're both negative here. And so think about if my original angle was here, doubling it apparently is landing in quadrant 3. Okay, it is possible that depending on how angled it was, that maybe doubling it could have landed me in another quadrant. But it appears as though I'm in this quadrant. So good stuff. And let's find tan 2 theta, and this will be the last little problem. Tan 2 theta is equal to 2 tan theta. Let's see, what was the value of tan the man? Negative 2. So 2 times negative 2 over 1 minus tan squared theta, so negative 2 all squared. So that's going to equal negative 4 over 1 minus, negative 2 all squared is positive, but this minus sign is still present. And so I've got negative 4 over negative 3, or 4/3.
Everyone is it's sine over the numerator of sine over numerator of cosine.
Yeah, for tangent, I could have just, you're right, done sine over cosine, and the denominators cancel out. So yeah, it's completely just the numerator divided by the numerator there, and that would equal that. So yeah, there are other ways I could have calculated that from there. But all right, friends, thanks for watching. Tienen un día el más bien del mundo.